Hey class! We're going to continue our work with matrices today, and as we continue looking at matrices, we're going to turn to what's called the determinant of a matrix, and so we're going to be looking at what a determinant is and how we can actually use this concept of determinants to solve a system of equations, which is exactly why we are doing this as part of our unit on systems of equations. So our learning goals are to find the determinant of both 2 by 2 and 3 by 3 matrices, and to use the determinant of a coefficient matrix to determine the number of solutions to a system. So every square matrix, which remember we talked about what that meant. It meant that it has the same number of rows and columns, so a 2 by 2, a 3 by 3, and so on, has an associated value called its determinant. Okay, shown by straight vertical brackets. So instead of using the sort of like, well, these would be, your matrix brackets, and that's how you show a matrix. And then, and the determinant brackets are just straight, and this is, we use the abbreviation DET. Now the straight brackets indicate, without actually having to write the word DET, that we want to take the determinant of that. Now what the determinant is for a 2 by 2 matrix, it's the difference of the product of the diagonals. So it's the difference, meaning we're subtracting, of the products of the two diagonals. And we talked in the last lesson about the main diagonal, but so it will be the difference between the product of the main diagonal and the other diagonal. So an example of that shown here in the orange box. So if we have the determinant 1, 2, or the matrix 1, 2, 3, 4, and we want to take its determinant, another way to write that is to just simply say, with the straight brackets, and we want to pick up on that subtlety. So if they're the straight brackets, that's another way of saying take the determinant. And what we would then do is we would multiply the main diagonal, the 1 by the 4, and that would give us 4, and then of the other diagonal, which would be these two, and that would give us 3 times 2, which is 6, and then we would subtract the 2, and we get a determinant of -2. So that's how you do the determinant of a 2 by 2 matrix, is simply multiply the two diagonals and subtract, take the main diagonal and subtract the other diagonal from it. And just a little note, you want to be careful not to mix up these the determinant notation with the absolute value. When we're talking about matrices, those straight brackets mean to take the determinant. So if I ask you to find the determinant of the matrix 1, 5, 4, 8, we would simply multiply the two numbers in the main diagonal, 1 times 8, and we would subtract from that the product of the other diagonal, 4 times 5. So 1 times 8 is 8, minus 4 times 5, which is 20, and we get a determinant of -12. So our determinant of that matrix is -12. So I want you to take a moment and try example B. So this one's going to be a you try question. Using that as an example, find the determinant of the matrix 1/2, -1, -1/2, and 2. You can turn the video on when you've completed the you try example. So there's the answer for the determinant of that matrix in example 1b. The determinant is 1/2. Let's turn the page. So the main reason why we are studying the determinant of a matrix is that you can actually use the determinant of a coefficient matrix to help you tell if a system of equations has one unique solution or not. And we can actually use the determinant in a process called Cramers rule to solve a system of equations. So from a system of equations, we can create what's called a coefficient matrix. So for example, let's say we came down and looked at example 2a here, and we had this system, 2x plus y equals 10, and 3x minus 2y is equal to 8. We could create a coefficient matrix by looking at the coefficients of the x's and the coefficients of the y's, and we would create a matrix. So in this case it would be a 2 by 2 because there are two x coefficients and there are two y coefficients, and that coefficient matrix would look like this. The two x's would go in the first column and the two y's would go in the second, and this would be what's called our coefficient matrix. Well, what the rule says is that if the determinant of your coefficient matrix is equal to 0, then that means you could have one of the two special case situations. You could have all real numbers, or you could have no solutions. So it really just kind of narrows it down as to whether it's one of the special cases or not. This would be if your determinant is 0. And if the determinant is not equal to 0, then that means there must be exactly one solution. Now, it doesn't actually tell you what the solutions are, but we do have a process for finding out what those are. So what about our example here? So if we found the determinant of this matrix, we multiplied the main diagonal, 2 times negative 2, and then we multiplied the other diagonal, and we multiply the 3 times 1, and 2 times negative 2 is negative 4, and minus 3 times 1, which is 3. So we have negative 4 minus 3, which is negative 7. And so what we can see is that because the determinant is not equal to 0, that we must have one unique solution to the system. So let's call this D. This is the determinant, and we got negative 7 for this. Now, how we can actually solve the system is by using this along with two other related determinants that are going to come from the coefficients in what's called a solution matrix. So we started off and we had this just coefficient matrix, and so when we found the determinant of that, it was negative 7. Now if we took that coefficient matrix, but instead of putting the x coefficients in that first column, if instead we took the two constant terms from the other sides of those two equations and substituted those in place of the x's, but kept the y's exactly the same, so as they were, 1 and negative 2, and we would call that d sub x. So it's the determinant where we replace the x column with the solution column and find the determinant of that. It would be, let's see, it'd be 10 times negative 2, which is negative 20, and then minus 8 times 1, which is 8. So it's negative 20 minus negative 8, which would be negative 28. And we could do the same thing, and we could create a matrix, or a determinant of a matrix y, which in this particular one, we would do the opposite. So this time we would replace the y column with those constant terms from the other side, and we would keep the x's the same, and we find the determinant of that, which would be 2 times 8, which is 16, minus 3 times 10, which is 30, and 16 minus 30 is negative 14. So now what do we do with those to get a solution? Because we said we were trying to get a solution, and it turns out what this Cramers rule says is this. It says the solution to our system, you know, it has two parts to it. It has an x and a y, that we can find the solution, the value of x, that is the solution to the system, by taking that d sub x, the determinant of where we replaced the x column with the solution, or the those constant terms 10 and 8, and we divide it by the original determinant d, and that'll give us our x value. And if we did that, and then we did the same thing with the y, where we took the determinant sub y and we divided it by the original determinant, that would give us our y value for our solution. So let's go ahead and do that here. So I'm going to take the d of x, which was negative 28, and I'm going to divide it by the determinant of the original coefficient matrix, and I get negative 28 divided by negative 7, which gives me a positive 4. There it is. I'll circle that. And then I do that same thing, but I take the y, that d sub y, which was negative 14, and I'm going to divide it by the original determinant, which was negative 7. I get a positive 2. And let's just go ahead and check that and see if that worked. So I'm saying that I think the solution is, and I know I'm writing all over this other example, so sorry about that, is I think it is 4, 2, and we could take that and plug it right back into that original system here and see if it works. So let's see if I put 4 in for x and 2 in for y in the first one. 2 times 4, which would be 8, plus 2, that equals 10. So it works in the first equation. Plug it into the second. 3 times 4 is 12, minus 2 times 2, which is 4, and 12 minus 4 is 8. So it turns out that that actually is the solution to that system. And I was able to do that by finding the original determinant, which I call d, finding the determinant of x, which is where I replace that x column. In fact, I'll highlight that. What I did was I just replaced the x column right here with those constant terms, but kept the y column the same. And then I did that exact same thing over here when I wanted to find the determinant of y, and I just replaced the y column with those two constant terms. And then finally did these two calculations, and they gave me the solution to that system. So we'll work through one more of those together before we end the lesson. And so if you haven't gotten all this written down yet, take a second and get any of these last minute things written down, because I am going to erase them so that we can continue on and do example 2b. Okay, so we said originally that the whole reason to even look at the determinant was to determine if a system has one of the special case situations, or whether it actually has just one single solution. And so the first thing we have to do if we want to use that determinant to tell how many solutions that the system will have is to put them both equations in standard form. So that means I'm just going to have to rewrite this really quick, and I'm going to bring this in the first equation, the 2y, to the other side to go with the 3x. So that makes it 3x minus 2y equals negative 5. I'll have to bring the 5 to the other side as well. And then in the second one, I'm going to have the negative 9x and the positive 15 switch sides. So I'm actually going to maybe bring the negative 6y over to be with the negative 9x. So it might look like this. Negative 9x plus 6y equals 15. I'm going to go ahead and set up that coefficient matrix real quick and just check it to make sure we actually have a single solution we could find. And we do that by taking just the coefficients, so that will mean that the 2x coefficients and then the 2y coefficients will create a matrix. And now we're going to calculate the determinant of that by multiplying the two diagonals and subtracting them. So 3 times 6 is 18. And negative 9 times negative 2 that makes a positive 18. 18 minus 18 is 0. So actually what this does tell me is that I am only going to, I'm not going to be able to get an exact single solution. This thing either has 0 solutions or no solutions at all. With that information, really all it just tells us is that it's one of the special cases. So this has 0 or infinite solutions. So what we'll do is we'll find some in our problem set when we meet in class again that are similar to example 2A, where we can actually go through that process of Cramer's rule and find solutions to a system. And then we'll also be in lesson 4.5 looking at another way, utilizing our graphing calculator to actually solve a system in just another method other than this Cramer's rule. So that's it for this lesson today. I'll see you in class.